Let's see, share screen. Okay, can you see my screen here?
Yes.
Okay, great. So my name is Henry Throop, and I am a senior scientist with the Planetary Science Institute in Washington, D.C. And I lived in India for 3 years, and I was very happy to be able to come to Kathmandu last year and speak at Southwest State College in association with the National Astronomical Society of Nepal. So I'm a member of the science team for NASA's New Horizons mission. I'm going to talk about work that we've been doing on the New Horizons mission, and including the flyby past Pluto and Ultima Thule. So for those of you who have seen my talk about Pluto, some of this material is the same as what we covered at Pluto. And then at the end, for the last 15 minutes or so, I'll be talking about the latest stuff from Ultima Thule, which is just results that we've gotten down in the last week or so, since we flew past Ultima Thule in the outer solar system. So for background, I want to start off, this is a picture of a galaxy. This is not our galaxy, this is someone else's galaxy. And this galaxy has about 100 billion stars in it. And our sun is just one average star in this galaxy. And you could put our sun in this galaxy. It's about halfway out, and it's just a normal star. Now there's, inside our solar system, we have this, we call it the solar system because it has the sun at the center of it. And we have the sun, we have Mercury, Venus, Earth, and Mars. We have, and these are the rocky planets. We have, and these we call the rocky planets because they are made of rocks and other materials that look like that around the Earth. And these are, you can walk on them, you can stand on the surface, and so forth. Outside of the rocky planets, we have Jupiter, Saturn, Uranus, and Neptune. And these we call the gas giant planets. And they're gas giants because they're made of hydrogen and helium gas predominantly, and they're held together just by gravity. And you can't walk on the surface of them. They don't have a surface that you can walk on. Outward of the gas giant planets, we come to Pluto, my favorite planet. Pluto's orbit is a little bit different than the other planets, but it still is orbiting the sun. And Pluto is just one of many bodies in the outer solar system. We have many lack of bodies in the outer solar system. Most of these are in what we call the Kuiper Belt. And the Kuiper Belt is this vast region of space in the outer solar system. And as you get further away from the sun, things get colder and colder. And so all these bodies are predominantly made of ice, because ice is not stable if you're right next to the sun because it's really hot. And so the further away you get in the solar system, the colder things get and the more ice you get. And so I'm going to talk about Pluto and the Kuiper Belt here. This is this kind of third region of planets, which is the icy planets in the outer solar system. Now, when I lived in Mumbai, this is a picture from the top of my flat, and we could see a lot of the solar system from one place in the on Earth. In fact, just on one morning, you could see the sun rising, you could see the moon, Venus, Mercury, Earth, Mars, Jupiter, Saturn, everything up in the sky. And people have, in fact, been seeing these planets for thousands of years. Now, it's hard to see Uranus, Neptune, Pluto, and the asteroids because they're pretty faint, but you can see all the other planets pretty well with your naked eye, just by using your eye without a telescope. Now, so I want to give you a little bit of a history of the discovery of Pluto and the outer solar system. So in 1874, there's a French astronomer, Urbain Le Verrier, and he was looking at the position of Uranus and found that, well, Uranus wasn't exactly where it was supposed to be. And he computed, he's using the laws of physics, Kepler's laws, to compute where Uranus should be. And it was here and here and here, and it was following a path, but it was deviating from that path a little bit. And he computed that it was that there was another planet which was gravitationally perturbing Uranus, and he computed that the estimated there was another planet out there. He said it should be this big, and it should be right here in the sky. And he looked up with his telescope, and he found it the next night there. And so that was one of the most remarkable discoveries in all of astronomy, where he predicted Uranus, or predicted Neptune, and discovered it almost the next day where it was supposed to be. Now, 30 years later, astronomer Percival Lowell in the US was looking at the position of Neptune. And he thought, wow, the position of Neptune isn't where it's supposed to be. I think that maybe there's another planet out there. And so he looked around and he said, well, maybe I'll find something else. Maybe it'll be called Pluto or Planet X. And he looked around, he looked around, he looked around. He thought he found something, and he didn't find it up there because he was looking in the wrong place. And then he died, and someone else was hired to take over for his job. And this other person used this telescope here. Clyde Tombaugh was his name. And what he did is a kind of a cool little trick. He looked up and he took a picture of the sky. And then the next day he took another picture of the sky. And I'm just going to go back and forth between these two pictures here. And things that move from one picture to the next are anything in the planets, or anything in the solar system, like planets, comets, and asteroids, move against the stars. Everything else that's not moving is a star, and that's why the constellations, like Orion, for instance, the constellation of Orion, doesn't move in the sky. Now it rises and sets, but all those stars are fixed in their position relative to each other during the night, and it's just the things like asteroids, comets, and the planets which move relative to the stars. So if you look closely here, you can actually see one body here which moves. I'll circle it here. It's this one right here, and it moves to right over here. And so this is actually the discovery image of Pluto right here. This is the very first time that Pluto was ever seen. And so this was covered in the New York Times in 1930 when it was discovered. And at that point, we didn't really know very much about Pluto. We know it's a long way away. Because it's a long way away, it's moving very, very slowly. You can use Kepler's laws to compute how fast it's moving relative to how far away it is. It tells you how strong the sun's gravity is. But besides that, we didn't really know much about it. So not much happened with Pluto for about 50 years until another astronomer, Jim Christie, was looking at it. And he saw that there was a little bit of a heavy spot on Pluto. And they see how there's a blob on one side, and then a couple days later on the right-hand side here, this blob has moved. And this is Pluto here, and what he suggested is that Pluto is orbited by a moon up here with this little blob which moves down to the bottom. And he said, hey, this is a moon. It's orbiting Pluto every 6.5 days, and I'm going to call this moon Charon. And so he discovered Pluto's moon Charon, and then and that was the first moon that was orbiting Pluto that was known about. So that was in 1978. Now astronomers since then have discovered a couple more moons going around Pluto. Nix and Hydra were discovered in 2006. In 2011, there was one called Kerberos, which was discovered. And then I was part of the group which discovered Styx in 2012 using the Hubble Space Telescope. That's kind of appropriate that we're studying the Pluto system from Asia. If you look at Pluto, it's just about the same size as India, and many of the other bodies in the Pluto system are kind of the same size as a bunch of the other countries around there. Pluto is about 2,000 kilometers across, and some of the Styx and Kerberos are just on the order of tens of kilometers across. So, just about the size of Kathmandu. But despite being far out, being far out actually makes it pretty hard to study Pluto. The best pictures that we have of Pluto is before we send a spacecraft up there, is something like these pictures here, where you can see Pluto, you can see Charon, but you can't really see any detail on the surface. We know that Pluto is, we know its rough size, we know how long it takes to spin around, we know a little bit about its temperature and its composition, but not very much. You can kind of put all you knew about Pluto before our spacecraft onto one slide. And to do more close-up viewing and to learn more about it really requires a close-up visit. So if you want to study Pluto or anything in the solar system, you can just use a telescope. So here's a nice telescope. This is a telescope in Ladakh. It's at 4,500 meters, and so this is one of the highest elevation telescopes in the world. And this telescope has a mirror 2 meters across, and if you want to build a telescope that has a mirror 3 meters across, or 4 meters, or 5 meters, you can do that. Just a bigger and bigger telescope. It becomes hard to build a mirror which is like 100 meters across, 200 meters, but eventually with a big enough mirror you can see things. But there's a better way to do that, because you don't really want to build a mirror that's 100 meters across, because that's hard to do. In the solar system, you can do a little trick. And instead of building a really big mirror and looking at Pluto that way, you just build a small mirror and you fly up to Pluto. You put it on a spacecraft and you fly it out there. And so that's what we're actually doing with our spacecraft mission. We have a small telescope and we fly it all the way out to Pluto and then beyond. And so this is our mission. This is a spacecraft. It's built by NASA. It's called the New Horizons mission. And so this is about 5,000 crore rupees. It's about the size of a small car, like a Tata Nano. It doesn't have any people in it. It just flies past Pluto. And it took pictures, and now it's going outward into the Kuiper Belt past Pluto. And if you look at it, the components on it, it's got a radio, it's got a battery, it's got cameras. In fact, it's kind of like you had a mobile. You have all the same things on this spacecraft as you have on your mobile. You click a picture and you hit send and you send it back to your friends. So it doesn't have to come back to Earth to bring any data back. It doesn't have to return film or anything like that. It just sends its data back over the radio link, just like if you were to take pictures, if you're on vacation with your friends and you take pictures and send them back to your family. We have a bunch of instruments on our spacecraft. There's the camera is the one called Lori, right in the middle here. That's our main camera. It's about 8 inches across, so it's about the same size as a camera that some amateur astronomers might have. You could buy a telescope like this for not too much money on the Earth. Then we have a UV spectrometer. UV means ultraviolet, and that's to look for Pluto's atmosphere. Then we have an infrared spectrometer, which is to look for the surface ices on Pluto. Down at the bottom, this is a really cool instrument. This is the student dust counter, and this is an instrument built by students at the University of Colorado. And so this listens for dust particles. It's kind of a microphone, kind of an amplifier that the spacecraft hits dust particles occasionally, and then this listens for them and picks them up. And then we have a couple of instruments to look for interactions with the solar wind at Pluto. So our spacecraft was selected for flight by NASA in 2001. It took us a couple of years to build the spacecraft. So 2002, 3, 4, and 5, we were building and integrating and testing the spacecraft. And then 2006, we took it down to Florida to get ready to launch. And so in 2002, here's just a couple of pictures of getting the spacecraft ready to launch. We're building it out of aluminum here. This is lightweight aluminum honeycomb construction. Here are people assembling the spacecraft, and this is the infrared spectrometer. So they're putting on the sensors and the thermal wrapping for our camera. Here they are putting on the wires for the antenna. This looks like surgeons and doctors with their baby here. And here they're doing spin balancing of the spacecraft just to make sure that it's balanced when it's spinning in space. Takes a big team to do this. There's about maybe 50 scientists on the mission, along with a whole lot of engineers and programmers and IT people and managers and program mission operators and cooks and writers and teachers and a whole suite of people who were involved with the mission here. So this is probably 2,000 people in total who've been involved with the New Horizons mission in building, operating, and flying it. Now, when I started working with this mission, I was living in Colorado. This is the United States here. Colorado is right in the center there, where all the mountains are. We started in Colorado. Some of the instruments were built in Texas, down at the bottom. Then some of the instruments were flown out to the East Coast near Washington, D.C., where they were bolted together at one of NASA centers, and then taken down to to Cape Canaveral, which is where the U.S.'s launches are from. So, and this is in early January 2006. We got the rocket, the launch vehicle. Launch vehicle is just a fancy word for rocket. So we got the launch vehicle there, and the New Horizons is actually inside that top unit that you see in front of you. That's the nose cone of the rocket, and then the main booster rockets are behind that. And if you look at how the rocket is built, it's basically just a flying fuel tank. That's the main thing that a rocket has on it, is just fuel. It's like a tube, and almost all the weight is liquid fuel, which is liquid oxygen plus kerosene. So you have to bring along your own oxygen to burn, because space doesn't have any oxygen in it. Other than that, it's just like an engine that you would have on Earth that's burning fuel and spitting it out. So we don't burn our engines the whole way going into the outer solar system. In fact, the engine only burns for about 40 minutes. After that 40 minutes, it's spent all of its fuel, and it's going fast enough. In fact, it's going about 50,000 kph that it can just cruise that whole distance out to Pluto and into the Kuiper Belt for the next 9.5 years in order to get there. Now here we are a couple of days before launch as we're wheeling out the spacecraft to the launch pad. And here we are here. You can see the spacecraft way in the distance there. It's not the one on the right, but it's on the left at the center. And let's see, here we are here, just all assembled to watch this. And here's our spacecraft, and it's gone off successfully. It's really exciting after 5 years of building the spacecraft to actually have it fly into the sky and see this before our eyes. It's a really emotional and exciting time. This is one of the geologists on the mission right here. This is one of the artists on the mission right here. And here we have a short movie. Now, I don't know if you can hear the sound here, but if you can see the movie, what I'm going to do is just narrate it as it's going along. So you can see the water tanks here and the lightning rods. That's just to protect the spacecraft from lightning. We're about 40 seconds before launch here. The spacecraft is getting ready to launch in January of 2006. Those are booster rockets on the side, so they just give it a little bit of extra kick. And so we're going through a status check, seeing make all the spacecraft systems are ready here. So we're doing a countdown: 11, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. So this is an extremely exciting time. Of course, it's really great to see this spacecraft go off. So it's just a magical time to see this spacecraft actually go up and be taking our spacecraft along on the rocket. So our spacecraft is New Horizons is the fastest spacecraft ever to be launched from Earth. And in fact, if you take the fastest car maybe you can buy on Earth, if you drive to the moon, it takes about a year to get to the moon. If you take the Apollo spacecraft, it takes about 4 days to get to the moon. We got to the moon, at the moon's orbit, about 9 hours. And that's because we're going really fast. Now, that's just cheating because we're using the laws of physics. Because we have a really small spacecraft and we have a really, really big launch vehicle, a really, really big rocket with a lot of energy. So conservation of energy tells you that if you have a low mass and a lot of energy, then you have a large velocity that you can get out of that. So that's what we did to get to Pluto so quickly. So it still took us 9.5 years to get to Pluto. So it's still a long trip out there, but 2007, 2008, 9, 10, 11, 12, 13, 14, 15. Eventually we got all the way out to Pluto. And during that time, we were keeping pretty busy. First thing we did is we actually flew past Jupiter. Jupiter was right on our path. We got to Jupiter about 1 year after we launched from the Earth. And we actually did a flyby Jupiter. We took some great pictures of Jupiter, the highest resolution pictures of Jupiter that have ever been taken. This is the highest resolution picture of Jupiter, and it's a great red spot that's ever been seen. Highest resolution global image of Jupiter taken in February of 2007, right about a year after our launch. Here's a movie of Jupiter's rings. You can see a couple of moons orbiting within Jupiter's rings as well, called Adrastea and Metis. This is Io. which is Jupiter's volcanic moon named Io. And it's pushed and pulled by the gravitational forces around Jupiter. So then it took us about 8.5 more years to get out to Pluto throughout the solar system. And we were pretty busy during that time, and that's because we just have one chance to go past Pluto, and then one chance to go past beyond that. And we didn't want to screw things up, so we wanted to spend all of our time testing our observation plan, calibrating our data, planning our observations, doing dress rehearsals, and so forth. Because what happens when we get out to Pluto is this spacecraft is a long way away, and we can't interactively drive it like with a joystick. This isn't a video game. Instead, what we have to do is we have to have a very carefully sequenced list of observations for it to take. It says, take a picture here, turn here, take a picture here, turn this way, slew this way, take 6 pictures, and so forth. And so we want to upload this entire sequence of observations and then have it run automatically when we get to Pluto. And so it takes a lot of effort to sequence this automatically. Because we want to optimize our science. We want to get the best possible science out of our observation of Pluto that we can. And that means trying to figure out where should we point the best? How do we aim it so that we can see both sides of Pluto? How do we set it up so that if there's interesting areas of Pluto that we really want to focus in, then we're going to be able to see those. It's how that we're going to be able to fly past its moons, going to get observations of the entire system of Pluto. How do we cram all those observations together in one plan? So we spent much of our 9 years trying to come up with the best science observation plan at Pluto. Then my involvement here, I was involved on the ground calibrating our spectrometer, our infrared spectrometer, before it launched. I did a lot of the development of software tools to plan our observations. I was involved with looking for dust that would be a hazard to the spacecraft and planning observations of dust and rings at Pluto. And then at Pluto and at Ultima Thule, I was searching for dust, searching for new moons, searching for rings in these systems. Now I want to mention one thing here. I mentioned that when we were selected by NASA, we just had one mission or one moon known around Pluto, which is the moon named Charon. But right around the time of launch, we had 2 additional moons that were discovered and called Nix, called Hydra. And then we had 2 more that were discovered after launch. One was called Kerberos and one called Styx. And this is really exciting because it means we get to fly past 5 moons instead of 1. But that's also kind of bad because it means there's a lot more stuff there. And maybe that's going to be a risk to the spacecraft. And I'm going to talk a little bit more about that when I talk about Ultima Thule coming up here. It does mean that we have to sort of change your observation plan because we want to fly by all of these things and study the entire rich, dense system of Pluto and not just Pluto itself. So we fly, we fly, we fly, we fly. We're going for 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years. Finally, by the end of 9 years, we're getting close to Pluto. And it's time to start using our spacecraft to look at Pluto. And you might be surprised by that. You might think that we've been using our spacecraft the whole time to look at Pluto, but we actually hadn't been, because our spacecraft, our telescope is really small. It's about this big. And the Hubble Space Telescope is about 2.5 meters across. So it's much, much, much bigger. And so Hubble can see Pluto pretty well with its 2.5 meter telescope. And we have to be really, really close to see any better than it can with our small telescope, with our 20 centimeter telescope. But by early 2015, we were close enough so that it made sense for us to start turning on our telescope and using it. And so this is one of the first images that we got back. And here you can start to see for the very first time, you can actually see details on the surface of Pluto. And you can see Pluto and its moon Charon, and you can see a couple of, now these might not look like exciting things to you, but you can actually see a couple of bright dots on the surface of Pluto, and these are more than you can ever see from the ground. It's more than you can see from Hubble Space Telescope, anything like that. And this is about 3 months before we actually get to Pluto. So for 3 months, we're seeing images like this, and they're just going to keep getting better and better every day. So this is about a month later. This is about, or 2 months later. This is about 3 weeks before we get to Pluto. Now it's up to, it looks like what, about 100 pixels across or so. You can start to see craters on the surface. Craters are formed on the surface of almost everything in the solar system. That's where you have impacts and where you have one body which slams into another one like a comet. or an asteroid. And if you look at the surface of the moon, we have craters all over the moon. We would expect to see craters all over the surface of Pluto as well, because it's an old body. It's been sitting out there in the Kuiper Belt for a long time. We're getting closer here. Here we are in late June. So we're about 2 weeks before the encounter, getting better images every day. And suddenly our images stopped. This is on July 4th, and our images stopped coming down. And we were actually uploading the final command sequence for our mission. And this giving it all of the commands and all the instructions to take pictures of Pluto. And suddenly our spacecraft vanished. So we're listening to it on a big radio dishes, big 70-meter radio dishes that NASA operates, and we just stopped getting the signal. And so we called up to the radio dish and like, hey, is there bad weather over there? Is that what's causing our signals to go away? And they were like, nope, the weather is fine. Your spacecraft has just vanished. We have no idea where your spacecraft is. So this is bad news, because we just have about 10 days before we actually get to Pluto, and our spacecraft has vanished. We don't know where it is. And so we looked around for it, and about 3 hours later, we found our spacecraft. And we found our spacecraft, and it had just rebooted itself, and it had gone into what's called safe mode. And safe mode is what the spacecraft does when something really bad happens to it. It reboots, and it comes up, and it basically calls us. And so it had called us, and it said that it was really confused, and it had just woken up, and it didn't know where it was, and it needed help from us. Now, sometimes your friends might call you. You get a WhatsApp from them like, hey, how you doing? Like, I'm really, out of it. Can you help me? I'm lost here. And so you WhatsApp back and forth with your friend, and you figure out what's going on. And but with New Horizons, you can do that too. But every time you send a message back and forth, it takes 8 hours round trip for that message to go and get to the spacecraft and be processed and be sent back to you. So you don't want to do that too many times, because we're closing in on Pluto. It's going to be just 10 days until we get there, and time is wasting here. So we want to do that just a couple of times. So we figured out what was going on, and we actually solved the problem pretty quickly. The reason why we solved the problem is our head of operations is Alice Bowman, and she's our mission operations manager. And she said she and her team of engineers figured out what the situation was. They found the spacecraft, they woke it up, they figured out what caused it to disappear, which was a software problem. We were asking the spacecraft to do too many things at a time. It was overtaxing its very simple CPU, and that caused it to reboot. But we now had to do a brain transplant. We had to upload new software, and this is just like uploading new operating system to your Android. But we had to do that to our spacecraft, which is 5 billion kilometers away, 6 billion kilometers away. And so we tested it on the ground, and we sent these new commands to the spacecraft to reprogram its brain. 2 days later, we were back on track. We saved the spacecraft, and we continued on our way to Pluto. Images kept coming down again, July 8th, July 9th, getting better and better every day. July 12th, we have 2 days to go until a close approach to Pluto. So let me tell you what's going to happen at Pluto. Now, we get to Pluto at just a little bit before 8 o'clock in the morning for our time on the East Coast. Now, we don't send back the images in real time because it takes a long time to send back each image. It's kind of like if you're on your mobile and you're sending back an image, but you just have one bar. It might take like a minute to send that picture. Well, with us, we have one bar, but it's getting sent so far with such a weak signal that it might take an hour to send a picture. We want to take like thousands of pictures, so it takes thousands of hours to send all these pictures back. So it's going to take like a year to send all these pictures back. And so we don't even try to have the spacecraft send back the images when it's observing. In fact, the spacecraft can't even send back the images when it's observing. So it's observing all day long. It's taking pictures all day long. It's not transmitting them to us. But we want to know how the spacecraft is doing. So at about 8 o'clock in the evening, we program the spacecraft to send us a signal. And we call this the phone home signal, kind of like in ET, right? Phone home. And so it phones us, calls us up, and it says, okay, I've taken data, and I've went through the Pluto system, and this is how the spacecraft is doing health-wise. And so that's what we've programmed it to do. So we fly past Pluto in the morning, and then we wait and cross our fingers, and then we hear from the spacecraft finally 12 hours later. So this is at the hotel in the morning where everybody's staying. These are some of the students on the student dust collector team. This is the crew from Discovery TV right here next to them. And here's our team at our Mission Operations Center. This is at the Johns Hopkins University Applied Physics Lab outside of Baltimore, Maryland, and outside of Washington, D.C. And so here's our team, and we are actually waiting to see the highest resolution image of Pluto, highest resolution global image of Pluto that has been seen. You want to see it? Let's see it. Ooh. So I love this image. I love this image. So this is the image that we've all been waiting for. And finally, for the first time, we see Pluto in high resolution at its real color. Is what Pluto would really look like if you were standing right in front of it. And you have Pluto right here. It's amazing. So what we see here is that Pluto doesn't look like the moon. I kind of expected Pluto to look like the moon. It's been out there for a long time. It doesn't have an atmosphere. It's been hit by a lot of asteroids and comets. You would expect it to be covered with craters. But it's not covered with craters. There's some craters on it. You can see a couple of impact craters. You see those round circles on there. Those are impact craters. And you can count, a couple of impact craters on there. But you don't see very many. You see some areas that, in fact, don't have any impact craters at all, like this area right in the middle here, which is, well, it's kind of a heart-shaped area there. And because we love Pluto and Pluto loves us too. Now, if you look around here, this is a picture of the moon. And this is an actual picture on the left here where the moon is just covered with all these craters. And on Pluto here on the right, you see a lot of the areas where there's no craters at all. And this is kind of like a truck. You're outside driving and you can see a truck on the road. And if the truck is really beat up, it's been out there for a long time. But if the truck is brand new and has no scratches on it, no dents, you're guessing it's probably a pretty new truck. And it's just hit the roads recently. But sometimes you can be fooled. Now, we think that all the planets were built at the same time. They're all 4.5 billion years old. But Pluto, even though it must be 4.5 billion years old, it doesn't have any craters on it, so it must have been resurfaced or repainted recently. And so maybe within the last 5 lakh years, it's been resurfaced. And so we don't know what's happening to it, but it looks like something is causing all the craters on Pluto to disappear. And maybe that's that the ice is melting. Maybe that's that they're being covered by something. Maybe that's that the Pluto is slowly flowing and creeping away. So all these craters just kind of relax outward. So we don't know it exactly, but Pluto looks like it's losing these craters somehow. And it's kind of like an old car, an old truck, which has been out on the road and beat up and then repainted to cover up all those craters. You can be fooled by that. And Pluto's trying to fool us too. Now this is the team. Just as we're looking at these images come down for the very first time, it's really just such a thrill to see these images and see these see this new world to explore and to discover. And I just love these. I'm just going to show you a couple of images of the team as we're looking at these new this first image of Pluto for the very first time. And I love these pictures just because these are geologists and they're just running their hands over the mountain ranges and running their hands over the craters and the valleys and so forth and trying to figure out all the physics, all the physical processes that went into forming Pluto and making it the world that we see right now, and arguing about different models. Oh, this must be formed by uplift. Oh, this must be formed by stretching and by cooling thermal cracks and so forth. Okay, so we get this. We spend the morning looking at these images, and then by the afternoon, the spacecraft is observing, and we're kind of crossing our fingers and hoping that the spacecraft is observing well. But we want to hear from it. We're supposed to hear from it in the afternoon. We're supposed to hear from it at 8 o'clock in the evening, and so we go out and we're waiting, everybody piles in a room. And so I'm not an engineer. There's a small room with engineers who are allowed who are actually typing on and talking with the radio. And so we were watching on TV the engineers communicating with their systems there. And this is Alice Bowman right there. Who's communicating with them. And so we got our signal down and we were really excited. You can see that picture there. That's actually the NASA spokesperson just before we got the signal and the same guy just after we got the signal. So it's a really exciting time to get our signal down. We heard the spacecraft was successful. It went through the Pluto system. It got data back, and its encounter was successful with Pluto. This is one of the geologists on the mission. Some of the other people on the mission. And what's amazing here is just how well our engineers do. It took us 9.5 years to go there. It's 6 billion kilometers away, and we got there 1 minute early. So we have here's another picture of Pluto here, and this is a picture of Pluto where we just changed the color, just exaggerated the color a little bit, and so you can see the differences in the different regions. And you can see some regions are kind of white. That means pure nitrogen ice. So all of Pluto, you know, you think of in the room that you're in or the room that I'm in, what's the air made out of? Well, the air is made out of nitrogen. It's made out of oxygen. It's made out of carbon dioxide. It's made out of maybe a little carbon monoxide, maybe a little bit of methane, things like that. And if you take those things, they all condense out. They all turn to snow. They all turn to ice. And so that's basically what Pluto is. It's made of the same stuff as the atmosphere here, but it's all turned to ice. And all these ices have slightly different colors, and that's what you're seeing on the surface of Pluto. Some of them are slightly bluish, some are slightly reddish, some are slightly orangish, some are slightly yellowish. And you're seeing all these different ices, but they're not mixed up. In fact, you know, down to the lower left here, you can see this big red portion, and that's probably organic molecules, kind of like soot, which is formed in the atmosphere somehow. And then other ices across the rest of Pluto here. Now, if you zoom in a little bit, this is in the heart, which we call Sputnik Planum. You can see these ice flows. These are kind of like ice flows in the Himalaya, where we see ice isn't really a solid, you know? We think of there being solid, liquid, and gas, but in glaciers, it's technically ice, but it can kind of flow and creep, and that's why it's really hard to climb up. Mount Everest is that the ice creeps and you have the ice falls and you have the glaciers that are flowing and moving and so forth, even though it's a solid. And the same thing is happening on Pluto. This is kind of like a bowl of, or like a bucket of chai, which is boiling, and it's turning over because there's heat from the bottom, which is causing convection and turning over. And that's not turning over every second, it's turning over every maybe 50 years or 5,000 years. But it's convection, it's heat from the center of Pluto is trying to escape out the edge. And it causes this ice to slowly convect and turn over. Now, here we see other things on Pluto. These are these tall ice mountains over there on the right. And you can actually measure the height of these mountains. Just look at their height of their shadows. You've maybe done lab experiments where you can measure the height of something by looking at the height of its shadow. Here, you can see these ice mountains are about 4,000 meters high. So this is half the height of Mount Everest, but it's on the smallest planet in the solar system. What's going on there? We see more mountains here, more water ice, more dark terrain here. And we see a couple of impact craters, but again, not too many. So this is a pretty new surface. There's no impact craters at all in this white area here. Moving over to Charon. Charon has this crazy surface. We see this huge crack going across the middle of it. And how can you get such a big crack like that? It has this mountain in a moat, which is in that zoom section there. And here's what we think is going on with Charon. We think it's probably due to thermal contraction. As things shrink or as they get bigger due to thermal changes, you can often get cracks. Like, look at a loaf of bread. You have a loaf of bread, it cracks. Same thing's going on with Charon. Now we have a lot of new maps of the features of Pluto and Charon that we're putting together. We're using for these suggestions from all across the world. It used to be in the past that we used suggestions just from American scientists, but now we're trying to use scientists and cultures and mythologies and explorers from all over the world. And that's one of the reasons why we're really happy that our largest mountains here are named, as you can see right there, Norgay Montes, followed by Hillary Montes as well. And to incorporate these Tenzing Norgay into the story of the discovery and exploration of the Pluto system. So we're really happy about that. Here again is another picture of Norgay Montes. and Hilary Montes, with Norgay being the tallest mountains that we see on Pluto, and just really beautiful terrain on the surface of Pluto that we're really thrilled to have found and named like this. In the background here, you can see all of Pluto's atmosphere. These are atmospheric levels. Sometimes you can see layers like this on the Earth in the atmosphere, especially at sunset. But here we see them on Pluto coming out really dramatically all over the surface. It's sort of surprised to see this. We don't know what's causing it exactly, but we're exploring it right now. Now, I predicted that Pluto would be cold, it would be dead, it would look like the moon, it would have a lot of craters, and pretty dead. What we found is actually something totally different than that. In fact, if you look at all of my predictions, they were essentially wrong. That my predictions, it wasn't dead. It wasn't really that. It's cold, but it's not like the coldest in the world out there. Because something is causing these craters to disappear, we don't know what's causing the craters to disappear, but it has something to do with heat coming from the inside of Pluto. So Pluto has a warmer surface inside, warmer core inside, and by warm, I don't mean that it's like you're not going to have a hot tub out there. So instead of being, say, 40 degrees above absolute zero, Pluto's maybe 50 degrees above absolute zero, but that's warm enough to be warmer than we expected. Still, you would freeze to death if you went there. The surface of Pluto is much younger, maybe 5 lakh years, and that seems like a long time, but it's much shorter than the age of the age of the solar system, which is about 5 billion years. We see mountains. They're forming right now. They're young. They're made out of ice. Glaciers are active. There's lots of chemistry on the surface. From any standpoint, people argue sometimes about whether Pluto's a planet or whether it's not. There's so much geology going on. There's so much more geology going on than many of the planets. So Pluto clearly is a planet from that standpoint. Then we see water. We see what we call organic molecules. Organic molecules are just things made out of carbon, hydrogen, oxygen, nitrogen. This isn't a good candidate for life. It's just too cold for life. If you want to find life, go somewhere else. There's many other better places to look for life, and we were not looking for life at Pluto. Okay, so it takes a couple of years to transmit all of our data. We have transmitted all of our data from Pluto, and it's now down on Earth. That's the end of Pluto. Now we have our spacecraft, and our spacecraft is right here. You know, this is the picture that I showed right at the beginning, and we passed by Pluto, and then what's after Pluto? Whoa, well, we're going out through the Kuiper Belt. What should we do there? And so we have this great spacecraft. We know it works. It's going through the Kuiper Belt. Let's do something. But we didn't know of any Kuiper Belt objects which were on our path. So we looked, and we actually used a bunch of ground-based telescopes, big telescopes on the ground, for a couple of years to look for a Kuiper Belt object. So another small icy body to fly past. And we searched and searched, and we couldn't find any that were on our path. Now we can steer our spacecraft a little bit. We can't steer it a lot, but we can steer it a little bit. So if we want to do a little divert maneuver to fly past a Kuiper Belt object, we can do that. We can't do a U-turn. We can't do a 45-degree turn, but we could turn by, a couple of degrees from our path. And so we couldn't find anything. Eventually, we kind of gave up, and we were like, there's only one telescope left on Earth that might be able to find something, and that's the Hubble Space Telescope. Hubble Space Telescope is a great telescope, but everybody wants to use the Hubble. And so it's really hard to get time on the Hubble Space Telescope. So we applied to get time, and eventually we did get some time. We got a lot of time on Hubble, and that was sort of our last hope, is that we had to get this time on Hubble Space Telescope in order to find a target to go to. Turns out we found 5 targets, and we found 5 targets that were near our path. 2 of them were a little bit too far away, and so we didn't have enough fuel to go to them. But 3 of them were very close to our path, and we decided to go past one of them, and we call that object Ultima Thule. And sometimes you see it called MU69, which is sort of the code name for it before it was given this name of Ultima Thule. And in this plot over here, you can see those circles. That's like a time-lapse plot, which is showing you the motion of Ultima Thule. It's going 1, 2, 3, 4, 5 in those steps. And so that's how we know that it's a planet in the solar system, or planet or Kuiper Belt object, is because it's moving relative to stars. Now, Ultima Thule is one of millions of small icy asteroids in the outer solar system. And these are a lot smaller than Pluto, and we've never seen any of these close up. So Pluto is pretty big. Pluto is thousands of kilometers across, 2,000 kilometers across. This thing is much smaller. In fact, it's only about 15 kilometers across. So it's by weight, it's about 1/1,000,000th of the size of Pluto. So Ultima Thule's on our path. We did a little targeting maneuver in 2017 to fly past it. But it's tricky to fly past it because it's really small and we don't know very much about it. In fact, I mean, Pluto is a really hard flyby. Pluto was the hardest and most distant thing that we'd ever flown past in the solar system. The only planet we'd never flown past. It was a 9-year trajectory to get out there with a extraordinary spacecraft. But Ultima Thule makes Pluto look easy. And that's because Ultima Thule is so much smaller. It's 1,000,000 times smaller than Pluto. It's 10,000 times fainter than Pluto. It's 2 billion kilometers further away from us than Pluto. And we don't know anything about it. We don't know its size. We don't know its position in space. We don't know its orbit. We don't know its brightness. And this is hard because when we fly past it, we need to point our cameras at it. And we're flying past at 15 kilometers per second. Ultima Thule is only 15 kilometers across. So if we're off by just 1 second, we might miss it entirely. And so it's extraordinarily difficult to do this. We want to know how bright it is because if we take pictures of it and they're overexposed or they're underexposed, well, you've done this with your cameras. If it's overexposed or underexposed, you can't see what you're looking at. What if we went out to Ultima Thule and we took pictures of it and they were underexposed and then we were like, oh, I guess we set the camera wrong. Maybe we'll have to go back, but there's no way you can go back. This is just a one-time thing. You fly past it and you can't mess it up. You have to get it right. But it's so hard to get it right because we don't know anything about it. Now, even the most basic things about it, its size and its position. How do you do this? Well, with something big, if you're trying to measure the size of Jupiter or the position of Jupiter, you can do that. You just take a picture. You can use Hubble or you can take basically any telescope can give you the size and position of Jupiter pretty well. Because Jupiter's close and it's bright and it's really, really big. It's tens of thousands of kilometers across. And so any telescope in the world can take a good picture of Jupiter and give you its size and its position. But if you're trying to look for something really faint and get its size and position, like Ultima Thule, it's almost impossible. Hubble spent hours and hours and hours just trying to detect Ultima Thule, and to try to measure its position very, very, very accurately is really, really hard. And this picture here behind the text kind of shows you what we're looking at, that these fainter stars just become fuzzier and fuzzier as they're fainter and fainter. And you need to figure out their position to 100 times or 1,000 times smaller than the size of a pixel, because the pixels are, only so small, and we need to have our resolution much, much finer than that in order to know its position close enough to fly past it. So you can't do this with Hubble, and you can't do it with any other telescope on the ground. But there's a really cool and unique way you can do it, and let me tell you about that and what we did. You can't do it with Hubble, but we bought a lot of small telescopes, and by small telescopes, I mean something about this big. And we rented some trucks, and we drove to the right time and place, and we watched the planet. We watched MU-69, Ultima Thule, pass in front of a distant star, and we watched it block out its light. And this was really, really hard, but it was the only way to do this. So here's what we did. I'll tell you a little bit about how this worked. We bought a lot of telescopes. We, in fact, bought about 25 telescopes. They're sitting in these boxes here. And we bought a lot of we rented a lot of trucks, and we went to Africa, we went to Argentina, and we went to South America to observe this object. And what happened is that occasionally, it's like a solar eclipse, So in a solar eclipse, the moon goes in front of the sun, and the moon blocks out the sun for about a minute or so. Now, you can't see the solar eclipse from anywhere on Earth. You can only see it from a couple of specific locations. Like last year, there was a solar eclipse that went across the United States. A couple of years ago, there was one that went across, southern India, and so forth. So you have to be in the right place at the right time to see the solar eclipse. Now, Ultima Thule was predicted to pass in front of a distant star, blocking out its light for a couple of seconds on one day, August 3rd, 2017. So this is basically a solar eclipse from the Kuiper Belt. It's not blocking out the sun, but it's blocking out the light of another star, another very, very faint star. And so what we wanted to do is we did our calculations, and we were like, well, we think that we can see this star if we're in South Africa over here, or if we're in Argentina over here. And so there's no, we couldn't use Hubble for this because Hubble's flying around the Earth. It's not going to be in Argentina. It's not going to be in South Africa. So we can't use Hubble for this at all. But what we could do is we could just buy a lot of these telescopes and put them on the ground there, drive out in trucks and set them up on the ground and watch this star disappear. And by watching it disappear, that'll tell us exactly where we're looking for the shadow. And then you can just invert that and figure out exactly where Ultima Thule is from where its shadow becomes visible. And so this is a bunch of us out in South Africa. We're on an ostrich farm in rural South Africa in a really, really dark sky. And our target is there, and we are observing Ultima Thule right now. And so we watch this star blink out for a couple of seconds. That was the idea. But did we see it? Nope, we had 15 telescopes and we missed it in every single one. It was really frustrating because we were in the wrong spot, and we actually were in 15 different spots, and all of our spots, they were up here in South Africa, and we should have been about 100 miles further away. But we didn't know that, but our calculations weren't right. But that's okay because, this is science. We're trying to learn this stuff. We're trying to learn where it was, and we didn't know. And so we went back to the drawing board, and we were like, okay, well, let's try in Argentina. And we missed it. We used 13 telescopes in Argentina. We missed it again. And then we're like, well, let's use Hubble. No, we can't use Hubble. But NASA has this Boeing 747 airplane, and it actually has a really big telescope cut in the side of it. And so you can fly this airplane up at like 15,000 meters. And so we used that airplane. This is a Boeing 747, and we put a telescope in it, and we observed from the middle of the Pacific Ocean. And we did see the shadow there. We were in the right place there. And then we saw it in Argentina with using 22 telescopes in Argentina. And so now we're starting to be successful. We went to Colombia the next year. We didn't see it from there. That's because it was rainy. That's what this picture here is from. And then we saw it in Africa the next year in 2018. It was rainy, but we saw it in a couple of telescopes. And so we saw the shadow. We saw this kind of solar eclipse of Mu-69. And that was enough to tell us a little bit about what its shape and size and position were. And here's how. Each of these lines here is the brightness in time from one telescope. So if the star, look at this top line, that just means the star is visible for the whole time, for like 1 minute long. And look at that next line there, the next line from the top. That just means the star is visible, and then it blinks out for a couple of seconds, and then it's visible again. And so these other lines, they all blink out for a couple of seconds also. And if you reconstruct this, you can kind of put together the shape of what Ultima Thule must look like to have a shadow like this. We're measuring its shadow from lots of different positions on Earth. And so we can guess at the shape and size of Ultima Thule. And it looks a little bit maybe like a blob of two spheres next to each other. Okay, so we have that. We know kind of where Ultima Thule is. We're getting close to it. In fact, this is in August. For the first time, we could see our target from New Horizons itself. So we're getting close to it. We have about 4 months until we get to Ultima Thule. And here's our first picture of it. A little hard to see there. So what I've done, if you look on the right-hand side, it's been enhanced, so you can see where Ultima Thule is. And I'm going to show you some pictures of it as we're getting closer to it. This is in August. This is in September. This is in October. This is in November. This is in December. Now with Pluto, it was getting bigger and bigger for months, 3 months. We could see it, and we could see features getting bigger and bigger. But with Ultima Thule, day after day, we were just seeing the same thing. So it's so small that even one day before we were supposed to get there, we were supposed to get to Ultima Thule on January 1st, on New Year's Day. And even one day before, it's so small that it was still just 1 pixel across. So this is a really, really fast flyby because it's a really, really small object. And so we only had 1 day of observing that was bigger than a pixel. So as we're getting closer there's also something which is dangerous that I want to tell you about, that we don't know what's around Ultima Thule. It's completely unknown. There might be rings around it. There might be dust around it, just like the planets, Jupiter, Saturn, Uranus, Neptune, all have rings, all have dust. Our spacecraft is going at 50,000 kph. At 50,000 kph, if we hit something just a millimeter across, that could be enough to destroy our spacecraft. And so dust that we can't see could be dangerous and it could end the mission. And so we can't see a single millimeter-sized dust grain on our path, of course, but what we could do is we could look for rings, we could look for clouds of dust, and we could actually use New Horizons itself to look for those. And so in early December, late November, I actually went to our Mission Operations Center to spend a couple of weeks using our spacecraft data to observe, to be on what we call the hazard team, which is to watch the space in front of us to see if there was any rings or any dust on our path. And so this is a picture of our building in the cold winter of Washington, D.C. That's our building in front there. And this is our group at work, and this is what we were doing for about 2 weeks straight, is we were taking pictures and we're analyzing them to see if there were any rings, see if there was any dust at Ultima Thule. And so each of us had computers there. Each of us were writing programs in Python to analyze these images and search them for anything that we could see on our path. After 3 weeks of doing this, what we concluded is thumbs up. We found nothing. We kind of wanted to find something because we're scientists and we wanted to find something. You know, it'd be really exciting to find some rings. But as far as safety of the mission is concerned, it was really good news that we found absolutely nothing at all. So we declared it safe to fly past Ultima Thule, because there were no rings there, no dust, and we were cleared to fly past it. Now, if we would have found some rings, what we would have done is steered out of the way. We would have still executed our plan, but we would have done it from a longer distance away from Ultima Thule, where it would be out in a safe zone. So we get to Ultima Thule. We do a countdown, and you know, this is New Year's Day that we're supposed to get there. New Year's Day, just 10 days ago, and so actually New Year's Eve, you know, it's New Year's, so we want to have it's exciting at New Year's Eve, and it's midnight, and we want to have a New Year's Eve countdown. But actually, we don't get there at midnight. Our spacecraft gets to Ultima Thule at 12:33 a.m. So midnight comes and goes. We ignore midnight, and we have our actual countdown at 12:33 a.m. And that's when our ball drops, because that's when we're doing a close approach to Ultima Thule, and we're flying 3,500 kilometers above its surface. And so at 12:33 a.m., we throw up the confetti and we start celebrating, because that's when we're close to our target. Now, the spacecraft is observed just like at Pluto. The spacecraft is observing for about 4 hours. We don't hear from it until it transmits a signal 4 hours after that, and then it takes 6 hours to get back to us. So about 10 o'clock in the morning, we finally received the signal from it. And it was successful. We successfully went through the system. We acquired data, and that took thousands of images after a journey of 6 billion kilometers in 12 years to the outer solar system. So you want to see our images from Ultima Thule? Okay. So first image that we got down. Now this is the first image that we got down. Doesn't look like much yet, does it? This is the first image which we could see that it was more than just a blob, more than just a point. So this is just before we got there. Next image, it's a little bit larger, getting a little bit larger on December 31st, getting a little bit larger still on January 1st. And then all these were taken right at close up, very close up, on December 31st, January 1st. But then the next day we got down, what we now have is the best image so far of Ultima Thule, which is on January 2nd. And so, so this is our first image of this brand new world. Here we are in the science team as we're watching these images come down on our display. It's a really exciting and emotional time to finally see this brand new small world emerging before our eyes. And look at that shape. Look at that shape. How well did that shape match? Well, this is one of our main scientists, Mark Bowie, and he's holding up a model that he made. This is a 3D printed model that he made 2 months before we actually got there. And he's holding that up compared with the actual image of what we really saw at Ultima Thule, and it matches perfectly. So our observations, done from a bunch of cheap telescopes in the back of pickup trucks, worked amazingly well to measure the shape and size and position of this tiny object from billions of kilometers away. So a definite victory lap for our observations, because this is such a hard flyby to execute, and we were extraordinarily successful in doing this. It's just a remarkable combination of an amazing team and ground-based observations and an amazing spacecraft. So what did we find out at Ultima Thule? So this is what's great here is we're going through the Kuiper Belt, and we're going through stuff which is old. Kuiper Belt is what we call the cold classical belt, which is a region of the Kuiper Belt, not where comets come from, and it's not where Pluto is. This is where the solar system formed. This is where the outer solar system formed. And these are bodies which we have never visited. And also these bodies have never visited us. They've never come in as comets. And so these are things which are, this is like a time machine. It's going back into the solar system for 4.5 billion years. And so these bodies here that we see, like Ultima Thule, have been frozen in a deep freeze for 4.5 billion years. They've never been touched out there. And so we're seeing the primordial building blocks that make up the solar system, that make up the planets. And we call these things planetesimals. And so what we see, here it is. It looks like a snowman. It's a small ball of ice and dust, about 30 kilometers across, made up of 2 balls, actually, and one a little bit bigger than the other. And maybe these probably merged with each other. You can tell actually that they didn't merge violently. You know, we kind of expected to see a lot of collisions, or some people would expect to see a lot of collisions in the outer solar system because there's a lot of bodies out there, but gravity is really weak. The gravity from the sun out there is really pretty slow, pretty weak. And so the velocities are really slow, and you can calculate this from Kepler's law that the speed of Mercury is really fast. But as you go further and further out in the solar system, if you go out to 60 AU, or an AU is the distance between the Earth and the Sun, its speeds, Keplerian orbital speeds, are really, really low out there. So so the speeds here are really, really low. And you can see these things didn't collide violently. They collided really gently. It's kind of like one spacecraft docking with another spacecraft, probably meters per second, not kilometers per second. And the surface looks smooth. It looks like there's no rocks on the surface. And this is really interesting. This object is spinning really fast. It actually spins around about every 4 hours. And 4 hours is actually fast enough that if you were standing on the surface, you would probably get lifted off the surface, just because the centrifugal force is higher and faster than the gravitational force. And so any rocks on the surface just get slowly lifted off the surface and blown away because of this centrifugal force spinning you off. 4 hours doesn't seem so fast, but it's actually really fast for the solar system. There's almost nothing in the solar system that spins that quickly, because that's fast enough to just destroy anything. Now, Ultima Thule looks a little bit like some other things we've seen in the solar system before. It looks a little bit like some comets, and you can see that all these, these are 3 comets over here. One called Halley, we know Halley's comet. One called Borrelly, and one called comet CG, which is an abbreviation for a longer name. And so these are the same sorts of bodies. Looks like these are all a little bit primordial, also, like CG, for instance. Looks also that it's made of 2 different bodies that have come together. But you can see where CG has a lot of cracks, a lot of texture, and so forth. And that's probably because it visited the sun. It came into our inner solar system, got sort of sublimated away from the sun by the sun, has all these vents and cracks and things like that on it. And so it's actually, it's much more processed than Ultima. Ultima is much more like it used to be for the last 4.5 billion years. It's been frozen, and the others have been worked on and active in the solar system for all that time. Now we still have a lot of mysteries of Ultima Thule. We don't know why there's just 2 bodies and not more. We don't really know how these bodies form. What's inside of them? Is this like other Kuiper Belt objects, or is it not? What's the geology going on? Why is this neck? You see this neck between the 2 bodies. Why is it lighter? What are these light spots on there? What are these cracks on the surface? So we're sending a lot of data back. We have, in fact, about 20 months of data that are still coming back. We've sent back a couple of images, but most of our data is still on board the spacecraft and slowly coming back to us. And so tune back in in about 2 years, and we'll have all the data back and we'll be analyzing it. Now, before all the data comes back, you can actually go online and all of you can download the images that we have. They're on NASA's website. If you search for Ultima Thule data download, you can download these images. You can start to do geology, process these images if you want to. Anybody on Earth can actually download these images and study them and become astronomers, just like do the same science that the people on the science team would be doing. So New Horizons is going to keep going. In another 15 years or so, it's going to leave the Kuiper Belt. It's going to go onward from there. We hope to be able to find another target to fly past in the Kuiper Belt. It took a long time to find this one. Maybe we'll be able to find another one as well. That'd be really exciting if we can fly by not just one Ultima Thule, but we can fly past another one after that as well. Eventually we'll leave the solar system, but we haven't left the solar system yet, and we're only about 1% of the way or less out of the solar system now. So there's a long way out in the solar system to go until we get to the next star. Eventually we do fly past the next star. Now, we can't really operate the spacecraft for that long. We're going to run out of fuel, run out of power before that, well before that time, and within probably the mid 2030s or so, we'll run out of fuel and power. But our spacecraft itself is going to keep on going, even if it doesn't have any power, essentially forever. So here's our team, and we're excited that we've done this well, and excited to keep our spacecraft going. Thank you so much. Thanks for all of your interest and encouragement along the way to go to Pluto, to go to Ultima Thule, and to keep on going. Here's our website. Here's my contact information, and thank you for having me here, and I'd be happy to take any questions.
Thank you, Dr. Henry. It was wonderful presentation with the insights on Ultima Thule. And in fact, we try to the replica of the distance communication using this Ethernet today. Before last year, we had you in person here in this hall, and today we have you through Ethernet. So we hope to hear more exciting news from New Horizons, and I hope the audience will be able to work on the science team during the master's or bachelor's program. Those who are at high school, they can work on the small project that they can contact you. We look forward to including.
Yes, okay. There was a little bit of echo, so I couldn't quite hear everything you're saying there. Okay. If you can maybe speak right into the microphone on the Zoom, I can hear everything.
Okay.
So thank you very much for joining. We couldn't see you, Henry.
Oh well, let's see. Let me put myself back.
Okay. Okay.
Here we are. Hello, hello.
So we will go for the question.
And please speak right into the computer so I can hear you.
Okay, I go out, so maybe it's because of two microphones together. Do you hear me now? Do you hear me?
Yes, I can hear you, but I can hear you most clearly if you speak into the computer, not the microphone.
So for that case, then maybe we can invite the person who wants to ask questions in front of this computer, or through microphone is okay.
Please.
You hear me loud, right? Here.
Yes, I hear you. I hear you right there. Yes.
Oh,
perfect.
okay. Okay then. Okay. So any questions from the audience to Dr. Henry about this New Horizons mission, Pluto, or Ultima Thule, or next flyby? We don't know. We don't know when the next flyby, right?
We'll keep looking. Yeah.
Okay. No questions? It seems everyone is happy. No questions.
All right.
Yeah, so please, at least few questions, because we still have few minutes left in our schedule. Okay.
Please.
You can be here. Yeah, you just come this side. Okay, now you can ask.
Okay.
Hello.
Hello,
Introduce yourself first.
my name is Asis, and why Pluto is declared as dwarf planet? I just want to know that. Why it is
Okay.
declared as dwarf planet? What was the reason behind it?
Yeah, okay, good question, good question. In fact, let me just show a couple of slides on that. Let me share here. Let's see. Okay, so the word planet has been, do you see the screen sharing now?
Yeah.
Okay, so the word planet has been used for thousands of years, and it was invented by the Greeks, and it meant a wandering star. And if we know anything about planets, we know they're not wandering, and they're not stars. But no one had ever really defined the word planet. And so sometimes planet referred to asteroids, sometimes moons, sometimes the sun was called a planet by various people. And so the word planet really hasn't really meant very much for a long time. And so you can come up with a definition for the word planet. And sometimes, you know, it was very clear when there were just 8 planets in the solar system that you know, all the planets were planets, and anything that wasn't a planet wasn't. And then we discovered Pluto, but then now we've discovered the Kuiper Belt also. And so the Kuiper Belt is filled with things which are a little bit like Pluto, but smaller, but still a little bit like Pluto. And so so there's lots of things which are, is Pluto a planet or not? Well, I mean, it orbits the sun, and it's big enough, kind of like the planets, and has a bunch of moons, and it has an atmosphere. We've already called it a planet, but it's also different than the other planets. It's smaller, its orbit is a little bit weirder, it's more like the other Kuiper Belt objects, and we don't call them planets. And maybe if we found Pluto today, we wouldn't call it a planet either. And so Pluto is definitely unusual among the planets. And so the IAU, the International Astronomical Union, tried to come up with a definition for the word planet. And you can read it here, but it's very difficult to come up with a definition for the word planet that includes all the right things and doesn't include other things. And so ultimately, it just kind of boils down to size. That things that are really, really big, like Jupiter, that's obviously a planet. And a dust particle, is a pebble called a planet? Well, no, because that's too small. And what about something which is halfway in between, like Pluto, which is, you know, 1,000 kilometers, 2,000 kilometers? Is that called a planet or not? And so it just comes down to size, that you have to draw the line somewhere between planet and not a planet. And some people draw the line so that Pluto is, yes, a planet, and some people draw the line so Pluto is not a planet. Personally, most astronomers, most solar system astronomers still call Pluto a planet. You can call Pluto a planet as well. There was a vote in 2006 about whether Pluto should be called a planet or not. They came up with the word dwarf planet, and they said, oh, you should call it a dwarf planet, but most people don't really agree with that. You can call it a planet, and just like a lot of astronomers still do.
Okay, so now I have one question for you, Henry. So how do we actually calculate this mass and size of the Ultima Thule?
Calculating its mass is pretty hard, because in order to calculate them, normally you can calculate the mass of Pluto pretty easily, because you can watch Charon go around Pluto. And the more mass that Pluto has, the faster it will pull Charon in orbit around it. But that's because Newton's law relates to the, that's because Newton's laws relate the mass of a body to how fast its satellite goes around it. But ultimately, we